let's just talk about factors that affect the reaction rate. All right. Now, when chemical reactions happen, in terms of kinetics, we're just going to be focusing on how fast. All right. How fast does this reaction occur? What is the rate of this reaction? Let's take a look at this. So, first off, if we increase the temperature of our reaction, we're going to increase the rate for that reaction. Okay. So, increasing temperature affects the rate of our reaction. Think about burning wood, for example. If it's super hot, more of the wood will be combusted and, more heat will be sort of generated, right? While if it's not so hot, well, less of the wood is actually going to react with the oxygen in the air to, be burned, essentially, quote unquote. Now, number two, surface area. If we increase the surface area for whatever reactants that we have, we're going to increase the rate for our reaction. Now, let's say if we have A is a solid, all right? This is some sort of particle, all right? And A is a solid. Let's say if we're reacting this with B, all right? Let's say if we're reacting A and B together. I put A inside of B, and I drop A into B. Now, the reaction is only limited to this area, right? Because it has such a tiny surface area. However, if I drop A into B, however, A is more sort of spread out, right? Notice how I sort of stretched out A a little bit. I stretched out this solid. So what happens is that this solid now has more surface area, and therefore this reaction can take place essentially anywhere in this container. So increasing my surface area increases the rate of my reaction, because now the reaction is not just limited to one area, right? It can be anywhere in this location right over here. And this is going to connect to collision theory, which I made a video on. But essentially, in order for particles to react, well, what happens is they have to hit each other. If you have a higher surface area, well, there's going to be a higher chance that the particles hit each other. All right, increasing concentration. And when I'm talking about increasing the concentration, or just dealing with concentrations in the first place, I'm only going to be referring to AQ or gases. All right, when I'm referring to concentrations, I'm either going to be talking about aqueous, aka dissolved in water, right? If I dissolve salt in water, the salt is going to be AQ, right? That means it's just dissolved in water. And gases. All right, whenever I'm dealing with concentration, I'm dealing with aqueous or gases. All right, that's very important. When we're talking about concentrations, we don't really talk about solids or liquids. The reason why is because the concentration of solids or liquids, they actually stay constant during a chemical reaction. Their concentrations do not change. All right, and I talk about this in the equilibrium constant video, so feel free to check that out. Anyways, let's just say if we're dealing with B in this case, right? Now, let's say if we increase the concentration of B, aka I add more of this solution. Well, guess what? This reaction is going to happen at a faster rate, right? If I add more B, well, that's just gonna make the reaction go, faster, because there's just more things to react with, essentially, right? And then finally, number 4, the addition of a catalyst. All reactions take energy, all right? Whether or not it's very little, all reactions have energy, right? It takes energy for some reaction to occur, and that energy is called the activation energy. Now, what the catalyst does is it lowers this activation energy. So essentially, let's just say if we have a reaction that's occurring, okay? On x-axis, we're going to have reaction progress, and on the y-axis, we're going to have potential energy. Now, for a reaction to occur, right, it's going to have to overcome a barrier of energy, right? And then after that, once it turns into products, energy is going to be released, and then it's effectively done, right? As bonds are being broken, energy is being absorbed. Hence why this is the upward hill, right? If we're trying to break bonds, that absorbs energy. So our potential energy is increasing here. But as bonds are being broken, as new bonds are being formed, right, that releases energy. New bonds forming releases energy, and therefore our potential energy is going to drop a bit. Now, in order for this reaction to occur, you have to sort of reach the top of this hill, right? From where you started to this top of the hill, this is the energy needed for this reaction to initiate, and that's known as activation energy. And what the catalyst essentially does is it lowers that. It provides an alternate reaction pathway. It's an alternate reaction pathway. All right, makes the conditions for this reaction very favorable. Let's say if we have a reaction where A reacts with B to form AB. Now the rate of the reaction, you can think about this as just how fast the reaction is going. And the rate of the reaction is going to be equal to K, which is a rate constant, multiplied by the concentration of A raised to the X power times the concentration of B raised to the Y power, where X and Y are our reaction orders. Now, just for a quick thing, so when you want to make a proportionality thing into an equation, all you have to kind of do is just add a constant. So for example, if rate in this case is proportional to concentration, right? The higher the concentration, the higher the rate, right? As concentration increases, the rate of my reaction increases because more particles are able to sort of collide with each other, and therefore the reaction is going to go at a faster rate, right? More products are going to be formed. Now, if I want to make a proportionality thing into an equation, I just add a constant. So in this case, K is going to be our constant that we add in order to make this into an equation. Let's look at this chart. So the rate of my reaction in this case is going to be in the units of molar per second. All right. So let's say if I start out with the concentration of A being 1 molar and the concentration of B being 1 molar as well. And the rate of my reaction is 1 molar per second. What that tells me is that every second that passes, 1 molar of A and 1 molar of B is being consumed. Now, let's say if I double the concentration of A. So let's say my concentration of A is 2 molar, and I keep the concentration of B constant. Let's say if the rate turns out to be, in this case, 2 molar per second. Notice how a 2 times increase in my concentration leads to a 2 times increase in my rate of reaction. And when that happens, the reaction with respect to A, so if we're just talking about the concentration of A, they call this first order. All right, so the reaction with respect to A, we say that this is a first order reaction, right? Notice how, right, the concentration of A, we doubled it. And it turns out that when we doubled the rate of our reaction, well, our rate doubled as well. So 2 to what power gives me 2? Well, 2 to the first power. 2 to the first power gives me 2, right? So that means that essentially you say that the reaction with respect to A, that's going to be first order. All right. Meaning if you double the concentration, you're going to double the rate. Now, let's say that if we're looking at B, all right, let's say if we double B's concentration and then we held A's concentration constant as the one in the beginning, all right. Now, let's say that when we do this, our rate jumps up to 4 molar per second. 4 molar per second. All right. So what does this mean? Well, notice how, right, when we doubled our concentration, our rate quadrupled. So 2 to what power gives me 4? 2 to the second power gives me 4, right? Therefore, you would say that for the concentration of B, you would say that the reaction is second order with respect to B. That just means that if you increase the concentration of B, well then the rate of the reaction is going to be, in this case, whatever multiplier you have, right? Whatever multiplier you have to the second power. If I were to, let's say, triple my concentration of B, keeping A constant, well then my rate would be 9 molar per second, right? So it always follows this pattern, this kind of exponential growth, right? If you increase the rate by 3 times, well then the rate is just going to be 3 to the second power, right, of what it was originally, and so on. Right? If you increased it by 4 times, it would just be 4 to the second power, and then that would just be a 16 times increase from what you had originally. So in this case, if I wanted to rate the rate of my reaction, it would be the rate of the reaction, that's going to be equal to the concentration of A, K, that's just constant, multiplied by the concentration of A, and that's going to be raised to the order of the reaction with respect to A. So notice how the order of the reaction with respect to A is first order, right? It's a first order thing. And then for the concentration of B, it's second order, right? The concentration of B, that's going to be second order. So my exponent is going to be 2. It's important to know that we get the reaction orders from the experiment that we do. So we get these values experimentally, okay? So this is different from the coefficients of our reactants. Oh, this is going to be held at a certain temperature. So this is going to be, let's say, at 330 degrees Kelvin. All right, we're going to, because of course, the rate of reaction, if we increase or if we decrease the temperature of our reaction, that's going to affect the rate of our reaction. So throughout all these experiments right over here, I kept the temperature at a constant. I don't know what that constant is. I'm just going to say, let's say, I'm making this up. It's 330 degrees Kelvin, let's just say. All right, we're doing all our experiments at a constant temperature so that we don't get any sort of error that's going on with our results, right? We're only looking at how the change in concentration impacts our rate and not anything else like temperature or anything related to that. Now, we can actually solve for the rate constant, all right? So we know that we can actually use the data from our table to solve for the rate constant. So let's just look at this row right over here. So when the rate of our reaction is 1 molar per second, notice how we have K. This is going to be equal to K. The concentration of A in this case is 1 molar, so it's going to be 1 to the first power. And this is going to be multiplied by B to the concentration of B to the second power. Well, the concentration of B at that moment is also 1 molar. All right. So this is 1 molar, and then this is another molar to the second power. So if we were to solve for K, we would just get that. So this is 1 molar per second. We get that K multiplied by, this is 1 molar to the first power. We have molar to the first power, and then this right over here is molar to the second power. So molar to the first power times molar to the second power is molar to the third power. If I divide both sides by molar to the third power, so this is going to be molar to the negative second power and seconds to the negative first power. All right, and there we go. There is the rate constant. And it turns out that no matter which no matter which row we use, if we use this row, if we use this row, or if we use this row, it turns out that we would actually get the same K value every time. It's really cool. Like you can use any one of these right over here, any one of these values in the same row, and you would get the same answer as I did right over here. So that is so when we're doing this, let's just say our original constant. Now let's say if I do this, right, I change my concentration here, and let's say my reaction rate actually does not change. So what do I do here? What happens here? Well, look, so you doubled the concentration, right? And what happens is the rate of the reaction didn't increase, right? It's still 1 times the original rate. So 2 to what power gives you 1? Well, 2 to the 0th power gives you 1. So that means this reaction is 0th order. You would say that this reaction is 0th order with respect to the concentration of C. All right, so it's all about looking at the 2 to the whatever power kind of relationships. I mean, you don't really have to. It's not always going to be 2 to some power equals whatever. If you kind of tripled the concentration, you would still get the same result. You would just have 3 to the what power gives you a 1x rate increase, and then you would still find out that x is equal to 0. So right, the 2 right over here, or the 3, those just represent your concentration multipliers, right? How much are you multiplying the original concentrations by? And then the 1 on the side, well, that's the rate multiplier, right? So there we go. Now, 0th order. Now, let's say for D, we increase my concentration by 2 times. So just notice how this is a 2 times increase while I'm keeping the concentration of C constant. I keep this concentration constant as what I had in the beginning. And let's say that if my rate increased, well, let's see, let's just say to 8. So notice how this is a 4 times increase. So when I increased my concentration by 2, well, I get a 4 times increase, right? A 4x increase in my rate, right? My rate was originally 2, then it went to 8 molars per second, so that's a 4 times increase. 2 to what power gives you 4? 2 to the second power gives you 4. So that means my reaction is second order with respect to D. And now I can rate my rate law. So my rate of the reaction is going to be my K value multiplied by the concentration of C to the reaction order. So notice how it's 0th order. Now anything raised to the 0th power is just equal to 1, so I don't even have to write that. And for D, it's going to be multiplied by the concentration of D raised to, in this case, D is second order, so it's going to be raised to the second power. And there we go. So this is going to be the rate law. Now the overall rate, the overall order of the reaction. So notice how we said that this reaction is 0th order with respect to the concentration of C, and we said this reaction is the second order with respect to the concentration of D. So you would say that the overall order of this reaction is just going to be 2. Right? The overall order for a reaction is just going to be the sum of the orders of the concentrations that you kind of found, the concentration orders. So for example, if we were to go back to my first example, right, notice how this reaction is first order with respect to the concentration of A, second order with respect to the concentration of B. So the overall order would just be 1 plus 2, which is 3, right? It would just be the sum of the overall it would be the sum of the orders of sort of each concentration that you're looking at. You can also think about it as it's just the sum of kind of the exponents when you write out the overall rate law. Now, the thing about K is that the units of K change based on the overall order of the reaction. So the units for the rate constant, they change based off of the overall order of a reaction. All right. So for example, let's just say if I have a reaction that's that's overall first order. All right. So let's say if my reaction looks something like this. My rate law looks something like this. Notice how overall the order of my reaction is, right, the first order, right, overall, right, because the only exponent I have is 1. Now, rate is always going to be molarity over some time period. Let's just say molar per second, or actually molar per time. All right, remember, rate of reaction, it's how much does your concentration change over a certain period of time. So my rate of reaction is going to be molar for every time. The units of K, I don't know, so I'm just going to put a question mark here. And we know that concentration is measured in molarity. So if I want to find out this mysterious unit, I just divide both sides by molarity. The molarities cancel out, and I get that the unit for K is just going to be the unit for K. That's just going to be 1 over time. So for overall first order reaction, the K value is going to be 1 over time. Now let's say if I'm looking at a reaction that's overall second order. So overall second order. Let's just say this is going to be rate is equal to K times the concentration of A to the first power multiplied by the concentration of B to the first power. So it's overall second order, right? Now, once again, rate is always measured in molar over some period of time. K, we don't know what that unit is. We know concentrations are always measured in molar, right? So we have 2 m's right over here. If we divide both sides by the 2 m's, right, aka m to the second power, these cancel out, and we get that the units for K, that's just going to be equal to 1 over molar times time. All right. Now let's take a look at a reaction that's overall third order. So if we have rate is equal to K multiplied by, let's just say, the concentration of A to the second power multiplied by the concentration of B to the first power. Notice how this is third order, right? Because overall third order, because 2 plus 1 gives me 3. Rate, once again, is molar per second, and K, that's just going to be, we don't know what that unit is. And notice how there's 3 concentration, right? There's molarity squared here and molarity to the first power here. So that makes up molarity to the third power here. If I divide both sides by molarity to the third power, I get that my units for K is going to be equal to 1 over molarity squared and multiplied by second. So notice how every time we add on molarity, right? Every time we add on like an order, like a increase by 1 in the overall order, notice how the molarity actually increases in my denominator, right? Every time my reaction order increases by a factor of 1, I'm essentially multiplying. You can think about it as molarity to the negative first power, right? Every time there's going to be an extra molarity in my denominator. And there's actually a formula, to represent this, because this is such like a nice relationship, right? That you can actually model this with an equation. So the units of K, that's going to be equal to molarity to the 1 minus the overall power divided by time. So for example, right, for the overall second order, let's take a look at this. Notice how K has the units of 1 over molar times time. If I plug in 2 into my equation for my overall order, right, notice how I get K is equal to m to the 1 minus 2, so m to the negative first power divided by time. M to the negative first, you can just move this to the denominator, so that's just going to be equal to 1 over molar times time, which is what I have here, right? And there we go. You can even model a 0th order overall order reaction. If the overall reaction is 0th order, well, notice how this is going to be K is going to be equal to m to the 1 minus 0, so just m to the first power divided by time. That's the units for a 0th overall order reaction. So yeah, units of K, they change depending on the overall reaction order. All right. The rate of my reaction doesn't change, and the concentrations doesn't change, right? The units for the rate is always going to be molar every time, right? Molars per time, some time period. And the concentrations always have the units molar, right? Concentration is measured in the unit of molarity. So if those two factors don't change, right? If these units right over here do not change, well, then the unit that has to change is going to be my rate constant. So, that's how you can think about it logically. And yeah, I hope you can put this formula to good use. Now, once again, remember that the rate is the change in concentration divided by our change in time, right? That's why the units for rate is going to be molars over some time period. It could be seconds, hours, whatever. But the rate of our reaction just refers to the change in our concentration of whatever we have divided by our change in time. Say that A disappears at a rate of 1 molar per second, right? Because A is a reactant, so it's going to be reacting, right? So the concentration is going to decrease, right? So we say that A is going to disappear at a rate of 1 molar per second. Well, by the same logic, that means that B is going to disappear at a rate of 2 molar per second, right? Based on the mole ratio, we're going to use twice as much B as we have A, so the concentration is going to be lost twice as fast, essentially. And by the same logic as that, well, we're going to say that AB2, that's going to appear, because remember, AB2 is a product, right? So the concentration is going to be increasing. So AB2 is going to be appearing at a rate of 1 molar per second, because the coefficient is 1, right? So we can use mole ratios, or these coefficients right over here, to help determine the rates of these individual components of the reaction, right? The rate of the product, the rate of the reactants individually, that's going to be different from the rate of the total reaction. So when I'm talking about the rate right over here, I'm going to be referring to the rate of the total reaction. And what do I mean by that? Well, is there any way to make all of these values equal? Okay. So the rate for the total reaction, that's going to be equal to negative 1 over A times the concentration of A divided by the concentration of T, aka the rate for A, right? When we're talking about the rate of something, it's going to be the change in concentration over the change in time. So that's going to be the rate for A, and that's going to be equal to negative 1 over B times concentration of B, blah, 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 blah. Okay. Now I'm going to try to break this down so that it doesn't seem too daunting. So the reason why we put a negative sign right over here is because we're dealing with reactants So for reactants, we're going to be losing the concentration, right? Our concentration is going to be decreasing. So therefore, we put a negative sign right over here. As for the products, we put a positive sign because, well, our products are being formed. So the concentration of that is going up. And then for A, B, and C, these are the respective mole ratios. So for example, if I were to write out the rate for whatever reaction that's going on here, it's going to be, all right, so negative 1 over A. A represents the coefficient of this term, right? So A represents the coefficient of this capital A, so it's going to be 1. And it's going to be multiplied by the rate for A. Now we said that the rate for A is going to be negative 1 molar per second, right? Because it's negative 1 once again because A is disappearing. I said A disappears at a rate of 1 molar per second. So that's why I put a negative sign here, right? You have to put a negative sign here up front and a negative sign up here. All right. Now, this is going to be equal to negative 1 over B. So B represents the little b represents the coefficient for the capital B. So it represents this 2 right over here, this coefficient. So negative 1 over 2 times the concentration of B divided by G. So we said how B disappears at a rate of 2 molar per second, right? So we're just going to put a negative 2 molar per second right over here, right? We're saying that the rate for B is going to be negative 2 molars per second, right? Because it's disappearing. Yeah, so yeah, essentially this concentration of the change in concentration of B divided by the change in time, that's essentially you can essentially see this change right over here, right? We're saying that the concentration of B changes by 2 molar every second. So 1 second is our change in time, and our change in concentration is 2 molar. So you can see by that. And then this is going to be equal to positive 1 over C. C represents the coefficient of capital C, so it represents, in this case, the coefficient of our product. I put a C here, but this basically just represents the product. If there were more products, then I could just be like, okay, this is going to be equal to positive 1 over D times the constant change in concentration of D divided by the change in time, right? I can just keep adding terms to however many products or however many reactants that we have. But in this case, because we only have one product, right, then we're only going to use one of the things here. So essentially, we're going to have positive 1 over C is the coefficient of this, so it's going to be 1. And then this is going to be times the change in concentration of D divided by the change in time. Well, we said how our products appear at 1 molar per second. So we're going to put 1 molar per second here, and it's positive once again because it's the products. And notice how all of these terms are equal to each other, right? Negative makes a positive. Negative 1/2 times negative 2 gives me 1. 1 times 1 gives me 1. So that means that the overall rate for this reaction is going to be 1 molar per second, and that is going to be our answer. And but before we get to the table, right, just note that the individual rates, so when we say that A disappears at a rate of 1 molar per second, we said how A disappears at a rate of 1 molar per second. So that's why we have this negative 1 molar per second here, right? It shows that our rate for A individually is negative, right? However, the rate for the overall reaction, is always going to be positive, because this right over here is negative because it's the reactant, right? And notice how we put a negative sign right in front of this equation. So therefore, negatives will cancel out and we get a positive value. All right, so for all of these terms, the rate for the overall reaction is going to be positive. Let's calculate the rate for the overall reaction using this table. So let's say if we have a reaction where A and B yields C, or A reacts with B to yield C, our products. Now, let's say at time is equal to 0, this is our initial concentration of A and B. However, after 10 seconds, you can see that our concentrations have changed. So I want to find out the rate of my total reaction, overall reaction, and I want it to be in the units of molars per second. So how can I do this? Well, my rate, that's going to be equal to negative 1 over A. So notice how for A right over here, All right, let's say if we have a reaction where A reacts with 2B to form 3C. Now, I want to write out my rate of my reaction in the units of molar per second because in my table right over here, I'm dealing with molarity and I'm also dealing with seconds as my time. So my unit for my rate is going to be molar divided by seconds. Notice how initially at time is equal to 0, I only have reactants. But after 10 seconds, well, after some time has passed, my concentration has changed. So notice how as my time changed, my concentration changed. And guess what? That's the rate of our reaction, right? Our rate of reaction is measuring how much does my concentration change over a certain period of time. So in this case, my rate is going to be negative 1 over A, so negative 1 over 1, right? Because the coefficient here is 1. So the coefficient here is 1. And that's going to be multiplied by our change in the concentration of A divided by our change in time. Now, in the previous problem, we saw before how it was very easy to find this value because we were given, this is essentially the rate for A. This is the rate for A. And that was given to us in the problem. But in this case, if we're given a table, we actually have to calculate it. So basically, our change in the concentration of A, that's going to be, hopefully you guys know how to calculate a slope of the line because this is very similar to that. Our change in A is going to be 0.300 minus 0.400, right? That's our change in A. How much has our A changed? And then the change in time in this case is 10 seconds. So if we put this into a calculator, we get that the rate for my reaction is going to be equal to 0.01, and remember the units for it is going to be molars over seconds. So that is going to be my answer. If you calculate this thing for one of the terms, then that's equal to the rate of the overall reaction. However, you could have done this with any other term, right? For example, if we were to look at the term for B, notice how this is negative 1 over B, so negative 1 over, and then our B is, the coefficient for my B term is 2, so I'm going to put a 2 here. Our change in the concentration of B, well, notice how the change in the concentration of B, that's going to be 0.600 minus 0.800 divided by my change in time. And when I put this into my calculator, I get negative 0.02 molar per second. Right, remember at the top of our equation, we're dealing with molarity. Bottom, we're dealing with seconds. So molarity over seconds. So I'm going to multiply this by negative 0.02, right? That's essentially this part of my equation. And notice how when you multiply them together, you still get positive 0.01 molar per second, right? So either way, if you use the products, if you use the reactants, it doesn't matter. The overall rate is always going to be the same. Now, in the first part of this video, we kind of explored how the concentration affects the rate of the reaction. So how the concentration affects the rate, right? The higher your change in the concentration, right? If your change in concentration is bigger, then that's going to lead to a higher rate, right? So next part of this video, we're going to be exploring something called the integrated rate law. Integrated rate law. The reason why it's called the integrated rate law is because it involves calculus. And one of the main parts of calculus is integrals. So if you guys do not know calculus, you could just skip this part of the video. But essentially, look, one more thing, by the way, the integrated rate law explains how time affects concentration. All right. So first part of the video, we explored how concentration affects rate. Once we're exploring the integrated rate laws, we're exploring how when the time passes, that's going to have an effect on how much concentration you have left, right? And we're going to be exploring half-lives, stuff like that, right? Because if you guys ever heard of half-lives before, it's basically just amount of time it takes for a sample of whatever, it could be whatever element you have for half of that to decay. So that's basically what we're going to be exploring in the later parts of the video. And as time passes, the amount of substance that you have left is going to slowly decrease. So our time is affecting the concentration when we're referring to half-lives. Now, what I'm actually going to do right now is, let's say if we have a reaction where A goes to B. All right, A reacts, just turns into B. All right, A just turns into B. So it's only one thing. Now, when there's only one thing in the reaction, by the way, it's something called unimolecular. unimolecular. So yeah, it only involves like a single molecule, right? Now, what I'm going to do now is notice how in the first part of the video, I said that the rate was equal to the rate constant multiplied by A to the reaction order, right? And for the second part of the video, I explored how rate is equal to this thing right over here. Because I'm lazy, I'm only going to do the proof for a first order overall reaction. So in this case, if we have a first order overall reaction, this is going to be K times the concentration of A raised to the first power, right? Because that's a first order overall. And it's going to be equal to, and I'm going to use this, right? Negative 1 over A times change in concentration of A divided by our change in time, all right? Now recall that the this lowercase a represents the coefficient of this big A. So because this coefficient is 1, I could just rewrite this as K times the concentration of A is equal to negative the change in concentration of A divided by the change in time. Now, change in something over change in another thing. Change in X, not change in X, change in Y over change in X. This sounds a lot like a derivative, right? A derivative, you measure a change in something, a tiny change in something leads to a tiny change in something else. So I'm actually just going to write this as negative dA over dt, right? For a tiny change in time, how does that affect the concentration change? All right, that's basically the way you express that in calculus terms. And now this is just going to be a differential equation. So if we multiply both sides by dt, so we get k dt is equal to, actually if I move the negative sign here, I get 1 over the concentration of A times dA, and then I integrate both sides. Now there's actually 2 ways of going about this. I'm going to do the first way. The first way we can do this is without bounds, and then the second way we can do this is with bounds. So the first way I'm going to be doing this is I'm not going to have any bounds at all. So this is going to be an indefinite integral. So if k is a constant, remember, so I could just move that outside the integral. So I get negative k times integral of dt, which is just t, right? And then the integral of 1 over something with respect to that something. Remember the integral of 1 over x, right? With respect to x, that's going to be ln of the absolute value of x. So this is going to be ln, and we don't actually need to use the absolute value actually, because the concentration is pretty much always going to be positive, or it's going to be 0. But either case, the concentration of something can't be negative, so I'm not going to put an absolute value there. It's going to be ln of the concentration of A, and then ln of the concentration of A, that's going to be plus C. Now let's try to solve for what C, our constant, is equal to. So when our time is equal to 0, so let's say if our time is equal to 0, that means that the concentration of my reactant is going to be equal to the concentration of the reactant at time 0, right? So when I'm referring to the concentration of A at time 0, I'm just going to put a subscript 0 there. And so this is what I'm going to get. So I'm going to get negative k. When my time is equal to 0, all of this just cancels out. So I get 0 is equal to, and then ln of the concentration of A, I could just put this as ln of the concentration of A, the initial concentration, right? And that's going to be plus C. So then, now after solving this, all in all, substituting it back, I get negative kt is equal to ln of the concentration of A minus ln of the concentration of A at time is equal to 0. Now, if I move this to the other side, I actually get my first order integrated rate law. I get ln, actually let me do this. So I get ln of the concentration of A, that's going to be equal to, negative kt plus ln of the concentration of A initially. All right. And when you take a look at that, we have our first order integrated rate law. Now, the thing about this is, notice how this is a linear relationship, right? Because it's in the form of y is equal to mx plus b. So our y value is ln of the concentration of A. Our slope is going to be negative k, negative of our rate constant. Our x value is going to be the same as our time, right? In this case, time is our x value. And we notice how as time increases, well, notice how this term gets more and more negative. So therefore, that basically represents that our concentration is going to be decreasing over time. And that makes sense, right? If we're talking about a reactant turning into a product, then it makes sense that as time goes on, we're going to be losing more of that reactant. So therefore, the concentration is going to decrease. And finally, initially, we start out with our initial concentration, right? Y is equal to mx plus b. This is essentially our y-intercept, aka sort of the starting point in our reaction, right? Where the reaction hasn't started yet. So we only have the initial concentration. If we were to put this on a graph, right, we could just put this on a graph. So our initial concentration, our y-intercept, is ln of the concentration of A at time equals 0. It's going to be a negative linear relationship, right, because it's negative kt. And then our x value, on our x-axis, we have time, right? Why did I put t there? Sorry, guys. On our x-axis, we have time, and our y-axis, we have ln of the concentration of A, right? This is just going to be the concentration of A after time has passed. Sometimes in books, you might see a subscript t here. It shows that this is the concentration of A after some time has passed, or at a certain moment in time. But yeah, this is kind of how it looks like, right? You start off initially here, then it's going to start decreasing at a slope of negative k, and then you notice how ln of this starts decreasing as time increases. So yeah, that monitors the relationship, okay? When talking about first order reactions, you want to be focusing on ln of A and time, how time affects ln of A. All right. There's actually another way you can actually do this proof. You can actually do this. So if I draw an arrow over here, right? Notice how we have the integral of negative k dt, and then after that, that's going to be equal to the integral of 1 over concentration of A dA times dA. Now, the thing is that we can actually put bounds on these. You might be saying, what? How do we put bounds on this indefinite integral? And let me show you what I mean. Recall that, what does this even mean? What does this dA over dt even mean? Well, what we're essentially trying to do is we're trying to find out how a change in time affects our change in concentration, right? A change in time causes a change in our concentration, right? So a change in time, well, I could just put a 0 on the bottom and t up top to indicate that we are integrating from time is equal to 0 to some time period, right? We're trying to find out how a change in time causes a change in concentration, right? So then the bounds for this integral would just be our initial concentration, and then the top bound would just be the concentration of A after some time has passed, right? So notice how this is our change in time. This is our change in concentration. So that matches up with what we were dealing with before. And now when we integrate this, it's going to be negative k and then t. And then this is going to be evaluated from t is equal. This is going to be evaluated from t is equal to t is equal to 0. So that's just going to stay the same, right? Because the 0 doesn't have an effect on this. And then when we integrate this, this is going to be ln of the concentration of A, ln of a concentration of A. And this is going to be evaluated from the concentration of A to the initial concentration, right? And because we're dealing with a definite integral, we're not going to put it plus C. So yeah. So then when we do this, we get negative kt is equal to ln of concentration of A minus ln of the concentration at time is equal to 0. If I move this to the other side, well, guess what? I end up with the same thing that I had before. ln of A is going to be equal to negative kt plus ln of the initial concentration. So yeah, there's 2 ways that you are able to do this. Actually, there's maybe you can change this up into the other form. I'm not. All right. Anyways, what I was saying is there is also like another form for writing out the first order integrated rate law. So let me go back here. So call that negative kt is equal to ln of A minus ln of the concentration of A at time 0, right? All I have done is I subtracted ln of A from both sides. So this cancels out to be, sorry. All right, so anyways, you can skip forward. So anyways, this is what we end up with. Now, if I subtract ln of the initial concentration on both sides, I get that negative kt is equal to ln of the concentration of A minus ln of the initial concentration. Using logarithm properties, log of A minus log of B, that's going to be equal to log of A divided by B. You can smash these two logarithms together because they have the same base. So because both of these are ln, I can rewrite this as ln of the concentration of A divided by ln of the concentration initially. That's going to be equal to negative kt. If I want to get rid of this ln, I raise both sides to the e power, so this cancels out. And then what I can do is I can multiply both sides by the initial concentration, right? So you notice how the ln cancels out, and when I multiply both sides by the initial concentration, that cancels out as well. So I get that the concentration of A, right? Because that's the only thing that's left on this side of the equation, right? Everything else has canceled out. The concentration of A, that's going to be equal to the initial concentration times e to the negative kt. All right, and this is also another form for the first order integrated rate law. I know. This is a lot. And you might be wondering, what the hell did I just do? Well, first here, this is a linear relationship, right? Notice how as time passes, that has a linear relationship with ln of A. However, if we were to monitor when time changes, right? If we want to monitor when time changes, what effect that has on the concentration of A, so without the ln, well, this is going to be an exponential decay relationship. So I'll just say that again. We're monitoring time against ln of A for a first order reaction. That's going to be linear. But if we're monitoring, actually I should say decreasing linear, right? Because remember we have this negative slope up front. But if we were to monitor time against just the concentration of A without the ln, this is going to be an exponential decay. It's a decay because this negative sign up front. All right. Now this is kind of like very similar to something you might have learned in algebra 2. This is I might have learned this in algebra 2, where you're doing compound interest, and this is compounded continuously. It's very similar to that. It's basically the chemistry version of that. Now, for a first order integrated rate law, notice how for the reaction that we're considering, notice how the coefficient of A is only 1. However, if the coefficient of A is actually 2, means that if there was 2A turning into B, my integrated rate law would be a little bit different. I would just have to put a 2 in front of the K, and that's all I would change. All right, so basically the amount of reactants that you have, so essentially the coefficient of your reactant plays a role in the first order integrated rate law. And actually, pretty much all the integrated rate laws will be explained later, but it's just a very tiny change, right? If there was, for example, 3A turning into B, well, then I would just have to put a 3 in front of the K. So then it's ln of concentration of A equals negative 3K now, but then nothing else changes, okay? So if you remember the general form for the integrated rate law, then you should be able to do it for any coefficient there is. The reason why this works is because now when you substitute 3 into my formula, and notice how when I do these steps, I'm going to end up with an extra 1/3 here. So then if I multiply both sides by 3, then this cancels out, right? And then after that, I'm just going to be left with extra 3 on top of the K the whole time. So that's where you get the negative 3K from, in case of the people who saw the proof and were wondering. Is basically the amount of time it takes for half a sample to sort of decay. So for example, if I have 100 grams of uranium, uranium is going to decay into other elements. So essentially, how long is it going to take for this 100 grams of uranium to become 50 grams of uranium, right? How long is it going to take for it to do that? And that's essentially half-life. Now, notice how when our time, actually, let me just, so in order for 100 grams of uranium to become 50 grams of uranium, it has to pass through one half-life. All right, and then half-life is symbolized by this T subscript 1/2. All right, so if uranium undergoes one half-life, this time period right over here, right, this amount of time, then it's going to become 50 grams of uranium. If it undergoes another half-life, then it's going to become 25 grams, and so on. Basically, how you express the half-life relationship mathematically. When our time period has reached our half-life period, the amount of the concentration of A that we have is going to be half. That's going to be half of what we had originally, right? So let me just substitute that all in here. So when time is equal to our half-life, so actually time is equal to our half-life, and we have e to the negative kt, but instead of t, we're going to have our half-life there. That's going to be our multiplied by original concentration. But then on the left-hand side of the equation, instead of the concentration of A, I'm going to substitute it with the initial concentration divided by 2. The initial concentration, half the initial concentration. All right, so this is essentially what we have. And we want to solve for the half-life. So how do I solve for the half-life? Well, first of all, I can just divide both sides by the initial concentration. So notice how this cancels out, right? If I divide both sides by it. So both these initial concentration amounts cancel out. So I'll just be left with 1/2 is equal to e to the negative kt half-life, where t is in our half-life. If I take ln of both sides, this cancels out. I get ln of 1/2 is equal to negative k, and then this is going to be our half-life. So then, if I divide both sides by negative k, I'm going to get ln of 1/2 divided by negative k, and that's going to be equal to our half-life. That's going to be equal to our half-life. Now, another exponent property that you can use is that, remember that if you have a logarithm, and let's say this is log of a to the c power, you're able to bring the exponent down. So that's equal to c times log of a. However, in this case, what we're going to do is we're going to bring this -1. You can think about it. We're going to bring that up. So this is the same thing as our half-life is equal to ln of 1/2 to the negative first power, right? It's like you brought this negative sign up into an exponent. That's going to be divided by k. So ultimately, the half-life for the first order reaction is going to be equal to ln of ln's not 0.5, I'm tweaking. ln of 2 divided by k. And there we go. If we want to find out an exact kind of value, if you want to use an estimate, ln of 2 is about 0.693. So that is an estimate that you could use. But if you have a calculator, just use ln of 2. There we go. The half-life for a first order reaction is going to be ln of 2 divided by the rate constant. So for example, I don't know, if my rate constant for a reaction, I don't even know, if let's say over seconds. So given the k value, solve for the half-life. Well, ln, we can just do ln of 2, and that's going to be divided by k, which is 0.1. So I'm going to get the half-life is going to be about, because that's going to be about 7 seconds. About 7 seconds. The units for our half-life is always going to be a time, right? 7 hours, 7 days, whatever. Half-life, this for a first order reaction is always going to be in a certain unit for time. And this is because for a first order reaction, recall that k has the units of 1/seconds. So if I have 1/seconds in the denominator, I can flip that back up, right? Because double denominator, right? And then I get the seconds is in the numerator. ln of 2 has no units at all. So essentially you're just going to be left with seconds or whatever time period you have in the numerator. And there we go. That is going to be our half-life. Notice how the half-life is not dependent on the initial concentration of whatever you have. It doesn't matter So for a first order reaction, the half-life is not dependent on the amount you start with. And that's actually the same case for a radioactive decay. So all sorts of radioactive decay, like the uranium thing I was talking about, right? The uranium thing, all of that is considered first order sort of radioactive decay, half-life, whatever, right? And the amount that you start with does not affect the half-life. For example, it does not matter if I have 1,000 grams of that type of uranium or 1,000,000 grams of a certain type of uranium. As long as it's the same type, like the same isotope, it's going to have the same half-life, right? Notice how the initial concentration does not affect the half-life. So only the rate constant affects it. So there we go. That all right. Now for the things we have learned in this video, we said that the half-life is equal to ln of 2 divided by k, and that one form of the integrated rate law for a first order reaction is the concentration of A is equal to the initial concentration times e to the negative kt. Now in Algebra 2 class, I also learned that if I wanted to calculate sort of how time affects concentration, there was another formula for that. And the other formula for that is the concentration after a certain time period is equal to the initial concentration multiplied by 0.5 to the time divided by the half-life. Now, this formula kind of makes sense because 0.5, when we're talking about half-lives, well, 0.5 is essentially our decay rate, right? We're losing 50% of our whatever we have, right? So when I saw these two formulas, I was like, what the hell? How can these two formulas yield the same result? That does not make any sense to me. So let me just try out a practice problem with both of these formulas to see if I get the same answer. Let's say if I start out with 100 grams of uranium, and let's say my half-life is 50 seconds. I want to find out how much uranium remains after 52 seconds. All right, seems nice enough. So let's get started using the first formula. Let's use it with the Algebra 2 formula first. So we know the half-life. For the half-life formula, it's going to be the concentration of, in this case, uranium after a certain time period. That's going to be equal to our initial concentration, or in this case, because we're talking about uranium, we're just going to be dealing with grams instead of concentration, right? Because we're talking about uranium, right? So instead of concentration, I'm just going to write grams of uranium, and that's going to be multiplied by 0.5, and this is going to be raised to the time divided by the half-life. Half-life is 50 seconds. So if I put this all into my calculator, 100 times 0.5 to the 52 over 50, that's going to be around 48.6 grams. This is going to be 48.6 grams. Screw the sig digs. Let's just pretend I had 3 all along. Let's just say I had 3 sig digs all along. All right. Now let's do it for the second way. The second way we can do it is using the chemistry version of the integrated rate law. Recall that half-life, in this case our half-life, that's going to be equal to ln of 2 divided by k. Now if I wanted to solve for k, this is 50 seconds, by the way. If I wanted to solve for k, I would get k, 50k. 50k is equal to ln of 2. Divide both sides by 50, right? Just rearrange the equation to solve for k. And I get that k is going to be equal to, so ln of 2 divided by 50. It's going to be like 0.0138. I'm rounding right now, so there's probably going to be a little bit of error. Actually, 139. All right, I'm rounding right now, so there's probably going to be a little bit of error that's going to occur, but we should get approximately the same answer. And yeah, the units for k is going to be 1 over seconds. Okay, now I just plug everything into my chemistry formula here. So I'm going to get the concentration of A after time has passed. Well, I don't know how much we have left, right? I don't know how much uranium that I have left, but I do know that I started out with 100 grams. It's going to be multiplied by e to the negative k, so we know k is 0.0139. And that's going to be multiplied by t, which is time. So the time that has passed is 52 seconds, right? And now I just put all of this into my calculator once again. So negative 0.0139 multiplied by 52. If I take e and raise it to that power, multiply that by 100, what the hell? I get 48.5 grams. If I did not round, I would get exactly 48.6, essentially. What the hell? I got the same answer. 2 different formulas. What the hell is going on here? Well, it turns out that this is actually pretty cool. So let me just, once again, I'm going to do another proof. But it's kind of amazing to see how these concepts relate to each other. Because at first, I was like, what the hell? How did these 2 half-life formulas relate to each other? I was curious. And then I just found out that, well, I know that the half-life is equal to ln of 2 divided by, our rate constant. Now, if I solve for the rate constant, I'm going to get K is equal to ln of 2 divided by our half-life. And let me substitute that in here. So I'm going to get time. Now, one thing that I notice is that this 2 right over here, what I can do is, I can essentially move this exponent up again. It's t divided by our half-life. All right. Now, one thing you might notice is that, well, I can use my exponent properties, and I can rewrite this as the concentration of A is equal to the initial concentration multiplied by E to the ln of 0.5. And then this is going to be to the power of t divided by the half-life. Right? This is just going to be an exponent property because we're essentially sort of multiplying the exponents together, right? So these two things are going to be the same. Now E and ln cancels out, and I get the concentration of A is going to be equal to the initial concentration multiplied by 0.5, right? That's what's remaining, to the t divided by our half-life. And there we go. This is how you get from the Algebra 2 version for the half-life stuff to the chemistry version. So yeah, when I found out about this, I was like, damn, this is pretty cool. And yeah, have a nice day, guys.